Good afternoon, everyone, and welcome to MOS Live. My name is Katie. My pronouns are she, hers, and I'll be keeping an eye out for all of your questions about light today. If you're watching on Zoom, you can ask those questions by clicking the Q&A button at the bottom of the screen, and you can leave your name and age. That way, if we get to your question, we can give you a shout out. If you'd like to see closed captions, you can click on the closed captions button at the bottom of your screen and select Show Captions. At this point, I invite my presenters to introduce themselves and we'll get started.
Hi, everyone. My name is Janine. My pronouns are she and her. And we were going to talk about one of our favorite emitters of light today. So one of my favorite emitters of light are stars, because we get to look out at them in the night sky and we get to learn all different kinds of things about space just by looking at their light.
Hi, my name is Meg. My pronouns are she and her, and my favorite emitter is a tricky one because I would like to say the moon, but the moon actually doesn't emit its own light. It is reflecting light from the sun, which goes, one of my favorite quotes from William Shakespeare is, "The moon's an errant thief, and her pale fire she snatches from the sun." So even back then, they understood reflected light from the moon.
That's so cool. My name is Megan, and my pronouns are she, her, and my favorite emitter of light are animals that emit light, things like a lightning bug.
Thank you so much, everyone. So our first question is from Jacob, who is 4 years old. And they ask, what is in a light switch box? How does it turn on? What kind of gadgets?
Well, so inside a light switch box, you find a switch. And basically what a switch is a piece of metal that's going to make contact or open and close a circuit. So the way we power things in our homes through our walls is from electricity that comes through our power lines into our houses and then up through the wiring inside your house. So a light switch has an open state and a closed state. And when you flip it on, you're closing. So all those electrons can run around in the circle through your light, turning it on and then back into the wall.
Thank you. Izora, who is 9 years old, wants to know, how does light travel? So I think we have one example that Janine just gave. Any others?
I'll take that one. So light is actually a set of oscillating waves. So there's, we call it electromagnetic radiation because there's an electric field that is oscillating and there's a magnetic field that is oscillating, and together they're traveling through space. And it's a kind of wave, sort of like a water wave, but it doesn't actually need anything like water to travel in, which is why we get light from the sun, which travels through the vacuum of space. But you can also send light through air, like how you're seeing us on your screen right now, or you can send light through other things like glass or like water. And the speed of light actually is just a little bit different in all of those different, what we call them a media or a medium. So the vacuum, the example of light from the sun, is the very fastest that light will travel. And it slows down ever so slightly if you shine light through air, and a little bit more in water and glass. So it's actually, if you think about light traveling, it's actually this sort of set of oscillating electric and magnetic fields traveling through whatever medium is in between you and what you're looking at.
Thank you. Adriana, who is 8, wants to know why, when you shine a light through a glass pyramid, it makes a rainbow.
That's a fun question. So a glass pyramid, like a prism, when you shine white light through it, and white light is made up of all of the different colors of light. So it's not just one color, it's actually all the colors. And so when you shine white light through a prism, as it moves through that glass or plastic, whatever the prism's made of, all of those different colors that make up the white light, they bend. And they bend just a little bit differently, depending on the wavelength of light. And so when that white light comes back out the other end, it's no longer just white light. All of those different colors that make up the white light have been in different ways. And so now they spread out into all the colors of the rainbow. And so that's why it can come in as white light and go out as a rainbow.
Yeah, just fun fact about that, I would say, is the natural phenomenon of rainbows are actually caused by a very similar effect, having to do with raindrops that are in between the sunlight and you. The raindrops are actually separating the light in the same way that the prism does. And that's why you see the same array of colors and they're all in the same order. So next time you happen to see, you're lucky you get to see a rainbow out there, you can think of that prism and it's exactly the same thing going on.
So speaking of rainbows, Clement, age 9, asks, why doesn't a rainbow have all of the colors?
So I'm not sure what you mean by all of the colors, because there are many colors that we can't see, right? So when we think about electromagnetism or light, the electromagnetic spectrum, that's a lot of different kinds of things, right? That scientists, physicists, and astronomers would all consider light. And we can see the light that's visible light. So that's your reddish color all the way through your violetish color. And so when we do see rainbows in the sky, it does have all of those colors across it. But when we color in rainbows to pick crayons and those kinds of things, you just pick a couple of the frequencies of light. What also is interesting is that depending on your source of light, you can actually have different rainbows. So for instance, astronomers who are looking at stars and trying to figure out what they're made up of will do this thing where they split the light coming from the star into the component colors to figure out what are the different wavelengths that are in that. And depending on that, you can actually figure out what elements there are. So like I have a favorite wavelength of light, which is the hydrogen alpha line. It's the first line in hydrogen. It's a bright red, and it comes out of hydrogen when the electron in hydrogen goes from its most excited state back to its ground state. So we'll talk about a lot of different things, and I'm kind of hopping through different topics within light, but light can both have a wave property and a particle property. And when it's a particle property, that's a quantum, a specific amount of light or a specific energy. And so when we see that in elements, we see that in colors. So some rainbows don't have all the colors because they don't have all of the elements in them.
Thank you. So I think that kind of gets to Mahira's question, who is 11, but just to recap, why do different elements burn different colors?
Yeah, just to follow up on what Janine was saying, different elements will burn different colors because they have electrons that are making up. Each element has a different number of electrons that orbit the nucleus of the atom at different distances. And when those electrons are excited, they hop up to different energy levels and hop back down. And when they hop back down, that's when they're releasing these photons. And those distances that they're hopping are at fixed levels, which is what we call quantized. And that results in the fact that they can only give off energy in these little packets that have the same value all the time. And those values correspond to the different wavelengths that we see. So you might have an element that gives off a bright red color, like Janine was just saying, and you might have, in that same hydrogen atom, you might have a different electron hopping from a different energy state down a shorter or a greater distance, giving off a higher energy packet of light than that red light, and then you might see that it's blue light instead. So just not to muddle what Janine was saying, but different elements, to sum up, burn different colors because they have these different energy level differences between their electrons.
Yeah, I like to think of them as kind of the thumbprint of the element. That element will always have, if you burn it, or you figure out a way to make it glow, it will always have those same colors in it. So if you find those colors, you've found that element.
And the way that we can see light in terms of heat too can have a lot to do with our perception, right? And correct me if I'm wrong about this, but when you say you're looking at something like a fire, right, which is really just our perception of like combustion, like a chemical reaction, and when you see things, when you heat them up and they're not quite as hot, and they're maybe, you see like a reddish or orangish light, and then as they get hotter, you may see like a more blue light, because blue light has higher energy, it's hotter.
Thank you. Let's see. Adam, who is 12, says, I heard that quantum teleporting is faster than light. How does that work? And is that true?
This is a super fun question and such an interesting one. And so when we talk about quantum teleportation, typically what people are talking about is using photons to carry information. And so recently, I think it was just a couple of years ago, there was a satellite that was launched into space by some Chinese scientists, and it was called Mycius. And it was used to teleport photons from Earth to outer space. And the way that they do that is by not necessarily teleporting the physical photon itself, but information that's been encoded in the photons, which is really cool. And the way that they do that is by using something called quantum entanglement, which is this link that can exist between two particles. So you can take two photons, or if you split a photon, the two resulting photons can be entangled, and they have this really close connection where if you do something to one, something happens to the other. So they can entangle two photons on Earth and send one up to outer space. And so now you've got one of the pair down on Earth and one up in outer space, but they're still entangled. And they can carry information. So basically, when you make a change to the one on Earth, that'll instantaneously change the one that's in outer space. And so that's kind of the teleportation part, where it's not necessarily that you're transmitting physical information, like you're breaking the laws of physics or something by going faster than the speed of light. It's just that these two particles have this correlation between them, where when you change one, you're going to make some sort of a change to the other one. And so by doing that, and those changes are related, so you can get the information that's encoded in the photon down here up to the photon up in space, and it happens instantaneously. And so that's kind of the teleportation part of it. So it's not necessarily that it's moving faster than the speed of light, it's just a completely different process.
Thank you. Is there light that is dangerous?
Oh, yes. Especially if you're talking about the whole electromagnetic spectrum. You can have very, very dangerous light. Even if you're thinking about you're going outside, you're going to spend some time in the sun, and you need to put on sunscreen to block yourself from those UV rays, right? Those are the purpler than purple. So if you look at rainbows and you think about just the visible part of the spectrum, you have red light to purple light. Over here, past red, you have infrared. All of this stuff over this way is less energetic, and all of this stuff this side of purple, purpler than purple, ultraviolet and onward, are higher energy. So these things can all start doing damage to you. So like if you've ever gotten an x-ray, if you've gone maybe to the dentist to get an x-ray on, and then they have you wear that lead vest, that's because there's very high energy particles, that are waves that are going through you to make that image, and they could do damage to your internal organs. So that's why we protect ourselves. We come up with all of these different things that can stop light wavelengths of light. So some things can be stopped just with a sheet of paper, and some things you need lead or even an entire planet in between you to stop them. So basically, I don't know, Megan, if you want to pull up that electromagnetic spectrum slide that we have, because it's basically anything that's past purple can be dangerous. And even things that are more in the visible spectrum, like don't look straight into a laser. It's not good for your eyes. But yeah, anything past that ultraviolet and onward, X-rays, gamma rays, radioactive elements, anything that's ionizing can do damage to your cells and can do damage to you. So wear your sunscreen.
Yeah. I would just add that, I mean, the question was about dangerous light, but for all of the same, well, many of the same reasons why some light can be dangerous, it can also be really useful in sort of tangible, touchy ways that you don't think of that light might be affecting things. So X-rays were one example that Janine just gave. There's also just regular light from the sun can be used to propel spacecraft, for example, because it actually does impart momentum to objects, even though it's not, even though photons are not matter, they still have momentum and they can actually push things around that way. So I think you can, if you search for it, you can find lots of examples of light, which you might just think of being sort of just around or being sort of ambient, but not interacting with you directly. There's all this dangerous side of things, like definitely you should wear sunscreen and don't look into lasers, but it has all of these neat applications too. Another example with lasers is just lots of neat quantum physics experiments where they need to heat something up or cool something down. You can use lasers for all sorts of cool purposes. And that's just light.
How do the polarized lenses on my sunglasses work? What do they do to light?
That's such a fun question. So light is traveling at you in a wave, right? But it can go in all different kinds of directions. You can imagine any direction you can think of, it can be coming towards you. What happens with polarized light is that basically you've given it a fence and it can only go through that in one direction. So anything that's polarized is light where the waves are all going in the same direction. So that's really helpful for, like, if you have polarized lenses and you're looking at water, you're going to reduce glare because only one of the kinds of light, on one of the directions of light is going to come back towards you. And usually the light that hits the top of the surface of the water and scatters is not that direction, although that might be backwards if anybody. I know it definitely scatters. I think sometimes hitting a surface can actually polarize light. So that's where it gets kind of confusing, but it's all going in the same direction and you're reducing glare by wearing those glasses.
If you have two pairs of sunglasses and you can't have the one in each hand, you could actually do a little experiment for yourself and figure out which way they're polarized, because I wish I had a pair of sunglasses. I'll use my glasses. If you had two pairs, you could just hold one up and then hold the other one up, rotated by 90 degrees. And you should see, if they're really polarized lenses, which they're telling you they are, you should see that all of the light disappears when you rotate them by 90 degrees. And that's because they're, like Janine was saying, they're forcing all of the light that goes through to be all in one direction. And when you're putting two pairs in front of each other, one in one direction and one in exactly the 90-degree direction, you're saying, nope, no more light at all. So you can run that little experiment at home for yourselves if you have two pairs of polarized sunglasses.
You can also do it, that reminds me, with 3D glasses. If you've ever gone to the movies and gotten those black 3D glasses, if you take the lenses of those, are actually, one is polarized one direction and one is polarized the other direction, and that's how they're able to send you two different images during the movie to get that 3D effect. So if you were able to overlay those two lenses, then you get that same everything's blacked out experiment, which is really fun.
Thanks. Mahiro, who is 11, again is asking, what's the difference between light and sound?
That's a cool question. And the difference is that there are two different things. So light is electromagnetic radiation, like Meg and Janine were talking about. And sound is a different type of wave. So sound travels in waves as well, but it's more of a disturbance in the air than light, which is more of a is actually energy. So light is energy and sound is not the same as that. You wouldn't say that sound is energy, right?
So one thing that's helpful to think about is sound is kind of stuff bumping up against each other and being transmitted that way, whereas light is kind of traveling through.
Yeah. So sound actually, it's a really big difference is that sound needs something to travel in, whereas light does not. So light will travel through just a vacuum of space. But sound actually needs air or water or something in order to achieve what Janine was just saying, because you actually need the molecules to be bumping up against each other to make the wave happen. Yeah, so when you clap your hands, you're actually making that sound is making all of the little air molecules bunch up right there, and then that bunched up air is or let me say that again. Then when the molecules that are being crowded together then spread apart, and the molecules that were next to them then hit each other, and that sort of compression travels through the air and eventually reaches someone else's ears, and they heard you clapping.
All right, we have actually a whole bunch of questions about space, which maybe we can finish off with a few of them. How does a black hole swallow light? Does a black hole swallow light?
I don't know if it really swallows light, and Meg and Janine, you're going to have to rescue me when I try to answer this question. But I think really what's happening is that in a black hole has an enormous amount of gravity. It's super, super massive. And so what that gravity really is bending of space. And so this space is bent to the point that it has all of this, a lot of gravity, because the black hole is so massive that it's bending space a lot. It creates a lot of gravity. And so even light that's trying to pass through there is affected by that gravity. And so it can't make it out. So it's not necessarily that the black hole is like a suction or something like that. It's the force of gravity that's doing that.
Yeah, we like to talk about gravity wells when we talk about things in space, because it's not like an active vacuum cleaner suction happening. It's the thing has been pulled down, and if you get too close to the hole, you're going to fall in. But if you're like going fast enough, you could go around it, you could orbit it, you could take a turn, maybe you diverge and come back. There's some really cool things that happen because of black holes and high amounts of gravity in space. So if you feel like looking up some pictures and doing some research on your own, check out an Einstein cross. That's really cool. And also sometimes you'll get like smearing of galaxies. So we're actually able to see galaxies that we wouldn't normally be able to see because of something called gravitational lensing, which also happens because of supermassive objects like that.
And Prisha, who is 8, asks, is the sun a light?
Yeah, that's a good question. The sun makes light, puts out light. The sun is a huge source of energy, and it's fueled inside the sun by the process of nuclear fusion. So the sun is actually so big that everything has gotten so squished inside it that the elements at the very center have started to combine together. And that's the process of fusion. So when two of the lightest elements, hydrogen, if you have two hydrogens and they stick together, they will become an atom of helium. And in that process, they release a lot of energy. So that's actually what's at the heart of the sun. That's what's powering it. And as a result of all of these fusion reactions that are happening inside the sun, it generates a huge amount of light. And that light sort of expands outward into space from the sun in all directions. And the Earth, we're orbiting over here, some distance from the sun, we're intercepting some small fraction of the total light that the sun is putting out. So I would say yes, the sun is a light, but it also generates light.
Thank you. And thank you so much to everyone. That is all the time we have for today. And I am so sorry that we did not get to each and every question, but we had so many because you all were such amazing scientists. So I hope you can tune back in next time. For now, I'll invite our presenters to say goodbye.
Bye.
Bye. Thank you.
And again, thank you to all of you who were able to join us today. If you did enjoy today's program, please visit engage.mos.org/welcome and support more programs like this in the future. And you can check for those at mos.org/mos@home. We'll see you next time. Thanks.